When we learned how to graph quadratics, we learned that there were basically three forms of a quadratic function that we had. We had standard form, we had vertex form, and we had intercept form. Now, to go from standard form to either one of the other two forms, we have to go through a process of simplifying. And the first process to go from standard form to intercept form is basically using the factoring method, and so sometimes the intercept is called the factored form. For vertex form, however, we're going to go through this process called completing a square. It's a little bit more complex. So what we're going to show you how to do here is to take the standard form of a quadratic equation and use the completing the square process so that we can make this in an easier form to graph. So if we look at example 3, y equals x squared minus 8x plus 11, we can't factor that. We're going to use the completing the square process. So you can see here we're going to actually kind of group, in the second step, we're going to kind of group x squared minus 8x kind of by itself and kind of shove the 11 to the side. Now, when we complete the square with the 16, it's important that we add that to both sides to balance this out. And then once we get the perfect square trinomial, we can move the 16 back over so that y is by itself. So you can see here that the vertex form is y equals x minus 4 squared minus 5. Now you could also see that in the form of f of x, because f of x and y mean the same thing. So go ahead and see if you can continue to use this completing the square process. We have two quadratic functions for you to complete the square and change the vertex form here. Okay, so the first thing I want to really do is I want to just kind of group these off. I want to complete the square for x squared plus 6x. And so in doing that, I'm going to end up adding 9 to both sides here. So I'm going to have x squared plus 6x plus 9, and I want those kind of grouped away from the 16. And then when I do that, I'm going to create a perfect square trinomial. So I have y plus 9 equals x plus 3 squared plus 16. And to get this in vertex form, I have to basically get the y by itself. So I'm going to subtract 9 from both sides, leaving me 7 on that side. So y equals x plus 3 squared plus 7. And if you recall from graphing quadratic functions in vertex form, this vertex would be -3 and a +7. So if you needed to do that, you could go that route. Now, for part B, I'd actually like to show you something just a little bit different. What if we had given this to you as f of x? Sometimes it doesn't look so great for us to add something to both sides. And so if I want to use this completing the square process without adding a value to the left side, I can still keep my equation balanced. And let's look how we do that. I'm going to group off this x squared minus 2x. And so in this case, I need to simply add a 1 to create a perfect squared trinomial. However, if I've added 1 to the right side and I haven't added it to the left side to keep it balanced, I need to somehow balance this right side out. And so the way that I can do that is I can actually subtract a 1 as well. And so subtracting 1 and adding 1 to the same side of the equation has the net effect of 0, and so I have not changed the value of the function. So I can continue along this route and say that f of x equals x minus 1 squared minus 5, and this is also vertex form. So just another way of looking at that, just in case you run into a problem like that in the future. Now we'll take a look at how we can use the completing the square method in an application problem. So if we look at sample problem number 4, what I'm going to ask you to do is to do your best to go ahead and work this first and see how far you can get through it, and then come back and see the problem worked out. And so I'm going to go ahead and work this now. If we notice, this toy company has a function that models the sales, and so the dollar depends on the price of the toys. Part A wants us to complete the square and write the function in vertex form so that we can graph it a little bit easier. So we're going to start off with this s of p equals -50 p squared plus 3000 and p. Now the first thing we want to do is in order to complete the square, our leading coefficient has to be equal to 1, which means we really need to factor out the negative 50. Now we have a value here that we can complete the square with. Now, this is going to be a little different than what we've seen before. If we complete the square here, I'm just going to take the c value as negative 60 over 2 squared, which gives us negative 30 squared, which is a positive 900. Now, we showed you in an earlier example that if we add a 900 without adding it to both sides, we technically also need to subtract that at the same time. Now, this is going to leave us a little bit of a different problem here, because really what I want to do is I want to be able to just have this 900 so that I can complete the square. But everything inside this parentheses is technically a multiple of the negative 50. So in order for me to get the negative 900 out of here, I need to multiply it times the negative 50. And so that will end up giving me something like this. Negative 900 times negative 50 is a positive 45,000. So I'm going to multiply that, kind of like distributing, but I'm only distributing one singular part of it. And so now I can actually write this in vertex form, and then we have the equation that we need. And so if we look at this very carefully, we have a vertex that is 30 and then 45,000. And it says to graph this. It says to draw your own scale for graphing. Complete the graph, draw your own scale. So in order to do this, it takes a little practice. I'll go down to a prior. So what I'm going to do here is I'm going to use my understanding of what this graph should look like. Now if we look at this, I can see that I have a negative there, and so my graph probably looks something a little bit like that, with the vertex being up here at the top. Now keep in mind here, this is representing dollar values, so really there's no need to come down into the negative numbers for the dollar values. We only need the quadrant 1 graph. Now it says to create your own scale. Notice that the 30 is representing dollars and the 45,000 is representing dollars, and so we need to create some sort of scale on each part as best we can, and the same thing on this axis. And so for the bottom axis, we've got maybe 10, 20, 30, 40, 50, and 60. On the top axis, however, I want to get to 45,000, so maybe I need to do this in 10,000 increments. And so we know that 30 and roughly 45,000 is going to give us 1 point, which is our vertex. The other thing that we really know is that if we have $0 in sales, and for our price, it's going to give us $0 in sales. And of course, we can use our understanding of symmetry here. So if our axis of symmetry runs through 30, then $60 price is also going to give us 0 in sales. And so our graph would look something like that, if I could get it right on the 60. Now, part B of this problem basically asks us what is the vertex of the function? And we already kind of defined that as 30 and 45,000. It says, what does the vertex represent? Well, the first part represents the price of the toy, and then the second part represents the sales that we would obtain with that given price. So at $30, I can expect $45,000 in sales. The second part, or this last part, the third part, says the model predicts that the total sales will be $40,000 when the toy price is $20. At what other price will it also be $40,000? And so if we look here, if we look at $40,000, $40,000 price level is roughly there. And we can see that, roundabout my scale, that gives me a $20 price tag. Well, if we know symmetry is working here, we should know that this other place that hits $40,000 in sales would be a $40 price tag. And so we can use our graph to do that. Or if we wanted to, so we basically could see that $40 in sales, a $40 price model will give us $40,000 in sales. Now we can verify that by evaluating at $40. And so if we plug this in either to our original or our new function in Vertex form, we can see that that's going to equal 40,000. So this just verifies what we could see graphically. Alright, so now you can see some word problems, how they can use completing the square to help us solve that as well.